Every time you store something to the cloud, or every time you have Grok or ChatGPT do a calculation, these are going through server farms that are filled with printed circuit boards. And those server farms replace out their printed circuit boards about every 3 years. So there are mountains of printed circuit boards that used to get shipped off to other countries for reprocessing. We have them right here. There's no need to be doing this mining and bringing all the heavy equipment first to identify the mine. It's hundreds of millions of dollars just to find the mine, and then hundreds of millions of dollars to start mining those and bringing in the equipment. So it's right here among us. That's what we call urban mining. Mining from what we've got right here, and that's what this company is going to be doing. Hi, I'm here with some friends of mine, Michael Walsh, who's the CEO of MTM Critical Metals, and the president, Steve Regal. And Steve is overseeing the U.S. entity that's called Flash Metals USA Inc. Flash Metals USA Inc. And Michael oversees the parent entity, which is MTM Critical Metals, which is based in Australia, and Steve is based in Houston. Now, the purpose of this is because many people ask me, how did I take my academic research and bring it into a company? And I've done this now many times. I think I've started about 20 different companies. 17 of them, I think, are going right now. And some of them we've combined together. Some of them are no more, but I think there's 17 right now. And so I'll take you through this because actually very few academics take their research and bring it into a company. So what I'm going to do is first take you through the science so that you understand the science of this. And then I'm going to go back to my two friends, Michael and Steve, and let them talk about the company and how we're bringing forth, they're bringing forth this company and how that was done. But I want to bring you up to speed on the science, first of all. And then through this, I'll discuss the sequence of what we went through to bring this academic research into a company. Now, prior to 2015, I used to license the technology that we would come up with. We'd file patents. So we come up with a discovery in the university. We file patents with the university. Everything that I do is owned by the university because I'm employed by Rice University. And I first write a disclosure that's then converted by lawyers into a patent application, and that is then filed, and it can be put on file as a U.S. patent only, or it can be a greater extent different parts of the world coverage, and you can select what domains you want, and that's what we do. And so every time you check off another country, it's going to end up costing you a lot more, so you judiciously choose what countries you want to be involved with. But within this, then we then look for financing and we start companies. And sometimes we run those companies for a long time as private companies. Sometimes we take them public very quickly by doing what we did in this case with MTM as a reverse merger with MTM. Sometimes we might use another method called a SPAC, but in this case, I believe it was a reverse merger. And so after I take you through the technology so that you understand what we've got here, then Michael and Steve will talk about the company and how they're taking that to the next level. If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together and I will share with you about why I embrace the resurrection of Jesus. Let's talk about the science here. And you'll see that this is flash Joule heating for metal extraction. Let me give you a background. Flash Joule heating sits in this domain of heating from milliseconds to seconds. We've done work before in laser-induced graphene, for example. These laser-induced methods usually running around the microsecond time scales. And you can see the temperature range at which these things reach. So laser-induced methods can even go up to 3,500 degrees, 4,000 degrees Kelvin. Now, when you're talking about thousands of degrees, a degree Kelvin is very close to a degree centigrade. in that you're only about 273 different. So when you're up at thousands, they're nearly the same. So when I say 3,000 Kelvin, I could just as well as say 3,000 centigrade. It's about the same. Flash Joule heating can get very hot as well, over 3,000 degrees, and runs for milliseconds to seconds. And then there's an area called chemical vapor deposition or hydrothermal treatment. And these run from seconds, usually minutes, to hours. And can be many hours, sometimes 6 hours, 12 hours. But that gives you the domain. But we're going to be functioning in this domain. And so what we came up with is another technology which I've talked about before on my site, and that's where we made flash graphene. But it's the same concept we're using here in this company. And the idea is you put with flash graphene, you put any carbon source between two electrodes, you apply a high voltage and a high current, and what happens is the material heats to over 3,000 Kelvin in 3 milliseconds. So very rapidly it heats up. And then it cools very rapidly as well. And people say, wow, you must put in an extraordinary amount of electricity. Actually, we don't. It's about $30 per ton in electricity. So $30 in electricity per ton. Now, there's a lot of salaries and other things around this and just running a factory. But the amount of electricity that's put in can range from $30 to $50 per ton. And what happens is every carbon bond in this material, whatever it is, whether it's coal or petroleum coke or food waste, whatever, will break at these energy levels. And so all the bonds break, and these carbon atoms then reassemble into the thermodynamically most stable system, which is graphene. If you add an iron catalyst, this will go to carbon nanotubes. So when you go to graphene, this forms this graphene, and that's under a company called Universal Matter Inc., which we started, which has remained a private company. And then we have another company that we've started, and they're making the carbon nanotubes in this way. You can start with lots of different sources of material. Now, we started a company that was this Universal Matter, and they started in 2019. It remains a private company. And here's the CEO, John Van Leeuwen, and the chief scientist, Dewey Long. Dewey is the one who discovered the flash Joule heating route to synthesis in my laboratory. So he's now with the company, and he's a senior scientist there. And they have entered these markets. They take graphene, they put them in cement and concrete, which allows you to use like 30% less concrete because you can add just a little bit of graphene, and it replaces all that compressive strength and tensile strength and the modulus. It's in asphalt as a complete replacement for the butadiene styrene rubber that's used in asphalt. It's in paints, coatings, and rubber tires, and they're entering other markets. So they've scaled now to about 1 ton per day production. So when people say, can this really scale? The answer is yes, and that's in a pilot facility. That's not the final facility, just their pilot facility. So what about flash Joule heating with chlorination for metal recovery, which gets to this work that we're doing with Flash Metals USA being the U.S. entity and MTM being the mothership, which is based in Australia, a mining entity in Australia. Here we're doing flash Joule heating under an atmosphere of chlorine, and I'll show you why that's important. Because we're trying to isolate metals. So what happens if you do flash Joule heating under chlorine, we're going to be capitalizing on what's called the free energy of formation of the metal chlorides. And whereupon the metal chlorides will distill immediately from this system. And so, for example, if you look at iron oxide is very high boiling, 3,400 degrees centigrade. If you reduce it to iron metal, that's still almost 3,000 degrees centigrade, 2,862 degrees centigrade. But if you do it under chlorine, that iron will react with the chlorine and form iron chloride. And that now distills at 315 degrees. So you see the dramatic declination in boiling point. And so we can bring it down to something that we can easily access now by making the chloride. Same thing with titanium, 3,000 degrees essentially at titanium oxide, over 3,000 degrees at titanium metal. But if you make the chloride, it boils at 136 degrees. And so this is how this technology works. So we're going to capitalize on what's called the free energy of formation of the metal chloride. So this is what the apparatus looks like in our laboratory. It's just got a thin little tube here. This is a 1-inch diameter tube. They still sell tubes by the outer diameter as 1 inch, 2 inch, 3 inch. And this is how historically the equipment was made. Here's a chlorine cylinder, and it fills up a little ballast here, and then we'll introduce chlorine into this reaction after we've purged it with an inert gas. We can go to a 2-inch tube. We can go to a 3-inch tube. And so you see, this is how we build them in the university. It goes actually from this, over time, we go up to a 3-inch tube, and then from this, it transfers to a company. And the company will start building up from there. And Steve and Michael will tell you about that transition and how they're carrying out that transition. But let me take you more through the technology. We were tasked by DARPA, we were contacted by the Defense Advanced Research Projects Agency a few years ago, and asked to separate metals from electronic waste. Now, you can do mining, you can work with ores, or you can say the metals are already here. They're already here in this country. They're all around us. They're not in the ground anymore. They're actually in our electronic devices and things. And so they wanted us to isolate indium, gallium, and tantalum from electronic waste. And it had to be from authentic electronic waste. And so what we did is we got some touchscreen displays. And on your smartphone, you'll see that this is indium tin oxide on your smartphone. And that's what makes that glass conductive. Glass is an insulator, but it's made conductive by putting a coating over it of indium tin oxide. So it's got indium. So indium is one of these metals. It's called a critical metal. It's one of these metals that we no longer mine in the United States, and it's all, even people who mine it generally, if it's mined, for example, in Australia, they're going to ship that off after mining it and send it to China for processing. But China is no longer selling us indium, gallium, tantalum, germanium, several different metals. They're no longer sharing with us. And because of that, we have to come up with our own sources of that. And so we can take these displays, we just put this in an oven and get rid of the plastic backing, and then you do an analysis by ICP mass spec and inductively coupled mass spectrometry, and you can look at the different metals and the different metal content. It's actually mostly gold in there and about 20% indium. Now, gold is a precious metal. It's not a critical metal, but it's a precious metal, so we want to get after this too. And here's what the thermodynamic plot looks like. So let me explain this to you. This is the free energy of formation of the metal chloride. And this is the temperature at which that happens. Well, gold is going to, you can do this at a lower temperature. It's going to, anytime you're less than zero, when the free energy is less than zero, it is a favorable reaction under atmospheric conditions. And at temperatures below about 250 or 300, gold will form the chloride. Now, gold won't stay the chloride because there's actually no stable, gold always goes to gold metal, and that's the amazing thing about gold. There's no stable oxidized states of gold stable at room temperature under atmospheric conditions, and that's why when there's a shipwreck from 500 years ago and you go to the bottom of the ocean and you find these gold bullion, they are as shiny under the ocean as they were the day that they were minted, because the gold doesn't form an oxide, and so it just remains gold metal and remains shiny, and that's one of the values of gold. But indium, which is the metal we're going toward, is that at about 630 degrees, this will start forming the chloride. And if we stay in a region right around here, we can pull out indium chloride without getting much of the magnesium, and without getting the gold, we can pull out the indium. So that's the technology. So here's all the different metal oxides that are in there after we bake this thing to get rid of the backing. And now we chlorinate and we can get the indium chloride. Now you'll get gold as well. You'll get gold metal will be there, but we get the indium chloride because the gold never oxidized up here. We get the indium chloride and that evaporates. So the indium chloride evaporates and we can capture that. That's what we were going after. But to get the gold, what we do is this is what's in the residue, and then we chlorinate again at a higher temperature, because if I go back here, you see at a higher temperature, all these other things will start to chlorinate, whereas gold won't chlorinate and chromium won't chlorinate. But there's not much chromium in there to begin with. And so what we do is we get this chlorination to occur, and gold remains there. These other two start distilling out, and then we get gold and chromium. Chromium was very little to begin with, but that's how we're going to isolate this. So when we heat this up, what we can do is at a certain voltage, and we have to test around a certain voltage, we can end up getting about 95% purity. We can get 95% purity at 105 volts. We get 95% purity, and we get 92% yield. And we can process about 180 grams per hour in our laboratory. So this is what we can get out of it. So we've isolated the indium from this, and then what we do is we go after the gold, and we were able to isolate the gold by the protocol I said to you, 96% purity, 82% yield. And that's again with just a laboratory, very simple apparatus. This is not optimized for industry. Industry would optimize from here. So then we started going after gallium. They wanted us to get gallium from waste. So here's a chip that has gallium nitride on it. And so we have to strip off these other layers, and we have to go after the gallium that's in there and try to isolate this gallium. And so we're going to try to get this gallium out of this waste. And you can see that gallium nitride will chlorinate. It's below zero at any one of these temperatures. But silver will also chlorinate. So both of these are going to chlorinate because the free energy is less than zero. The silicon and the gold will not chlorinate at these temperatures. So silver and gallium, say if we were at this temperature, we'd get silver and gallium. But it turns out that the silver chloride boiling point is very high. It's 1,500 degrees. Whereas gallium chloride boils at a much lower temperature. I don't remember, a couple hundred degrees or something like that. And so you take this LED manufactured waste, you do the chlorination, and gallium chloride will come distilling out. Silicon never chlorinates. Silver is a very high boiling, so we don't get that, and we get the gallium chloride. So what we can do is we get 97% purity, 86.5% yield on the gallium. So we've isolated gallium. And then we went after tantalum. So we just buy these used capacitors on eBay. These are used capacitors. They look like little pieces of candy. They're covered in plastic on the outside. We pyrolyze it. That gets rid of the plastic, and we're left with the metals. And here's all the different metals that are in tantalum capacitors. Here's the tantalum that's in there. It's like 37% tantalum. You have a lot of silicon in there. And then here's the other metals. So how are we going to isolate that? All of these in this pyrolysis turn to the metal oxides. And so you can see that there is a window here where everything that's below zero is going to form the metal chloride. So all of these are going to form the metal chloride except for silicon and tantalum. Neither of these will form the metal chloride. So that will get rid of all of these and leave just silicon and tantalum. Now remember, there's a lot of silicon in there, so we've got to get rid of that. So we can do what's called a carbochlorination. We add carbon and chlorine, and the carbon at these temperatures will reduce the metal from the metal oxide to the metal zero species, and then the chlorine will react with the metal zero species. And so carbochlorination, here's the delta G plot, they're both below zero. So how are we going to separate these two? Because at all temperatures, both of these under carbochlorination are going to end up chlorinating. Well, then what we can do is we can go in a lab and do what's called an Arrhenius plot, and we can test silicon oxide versus tantalum oxide and test how rapidly they would form the chloride. So this is not can they form. This just tells you can they form. The answer is yes. This tells you how rapidly they form. This is an Arrhenius plot. And it turns out the activation, the energy we need to put in for tantalum to form is 31 kilojoules per mole. For silicon to chlorinate is 53. So we can hit this without ever reaching this. So kinetically, this is faster. So we're going to grab this out kinetically. And so here's the protocol. You have all these metal oxides. You chlorinate everything except for tantalum and silicon. That remains as the residue. These evaporate away. Then you take that residue, you add carbon, and you do the flash Joule heating at 1200 degrees, kinetic control, and you get the tantalum chloride. Silicon remains as the oxide. Tantalum chloride comes distilling out. You expose it to air. You goes to tantalum oxide. And then what we can do is we end up with more than 95% purity, more than 86% yield of the tantalum. So we've got those three metals. And here was the plot that we presented to DARPA after 15 months of funding. These were the goals that they had for us, and in every case, from real waste, we could hit their purity and their productivity rate. We had both purity rate and productivity rate, so we could hit that. So we demonstrated that with all of those critical metals. And then what we've done is we've gone on and we've said, okay, what about, you've heard about rare earth elements, and there's a lot of rare earth elements in catalysts and in other ceramics and things, but very high concentrations of rare earth elements are in magnets. So a lot of used magnets that once they're used, what do? Well, we can get the rare earth elements back out of these. And so what we do is, here's the traditional way of getting the samarium back out of a samarium cobalt magnet. All of these different steps and all of these recycling steps. It's a very long protocol. Well, we could reduce that to a very short protocol because I just bought these samarium cobalt magnets from Amazon, and we do the calcination and grinding. And then what will happen is, if you look at the plot here, everything that is less than 0 is going to form the chloride. And so what we're going to do is we're going to get the cobalt, the iron, and the copper to form the chloride. And the only oxides that are left up here are going to be the zirconium and the samarium. Samarium is the rare earth element. Zirconium is just a trace to deal with anyway. There's not much in there anyway. So this samarium cobalt magnet has somewhere here, somewhere about 18% samarium, and it's about 67% cobalt. And so there's more cobalt in this than samarium. Cobalt's a magnetic metal as well. And so we go through this flashing procedure, and we can get the samarium out in 94% purity and 95% yield. So this is taking waste and getting the rare earth elements out. You've heard of all this rare earth elements, these deals with the Ukraine and all of what we have to do. We already have them here. If we would just realize that we have the rare earth elements already here, we don't have to do so much mining. We don't have to fight wars over this stuff. It's already here. Instead of just throwing away our waste or sending it to Africa, we just keep it right here and we do the recycling. That's what this company is going to do. It's going to take this technology and just recycle it. And metals are infinitely recyclable. Unlike plastics, if you recycle a plastic, you take polypropylene and you turn it back into polypropylene. You can never use it in food products again or pharmaceutical products, and it's an inferior product to virgin polypropylene. Not so with metals. Metals just go right back to the metals, and so they're infinitely recyclable. It's just changing the mindset, and we don't have to fight wars over this stuff anymore. And so here we did the same thing with neodymium iron boron magnets. This is a rare earth element magnet. Again, bought these magnets from Amazon, and here's the thermodynamic plot. Here's the window that we're going to go after, and we're going to be able to evaporate these, and we're going to go after the rare earth elements. And there's a number of rare earth elements in this. There's the cerium, neodymium, and then here's another rare earth element and another rare earth element, so that we can go after these. And what we can get is this reaction to go, and what we get here is 98% purity of the rare earth elements. So we get the rare earth elements back in 98% purity, 95% yield. We grab out all of these rare earth elements. So all of these wind turbines, all these things that have the rare earth elements, we get all these back. So that's what this company is going to be doing. What about from ores? If you wanted to do it from ores, if you didn't want to do it from waste, if you wanted to do it from ores, here's an example where it makes sense that you might want to do it from ores. This is getting lithium chloride from spodumene. Spodumene is a mineral, and it's lithium, aluminum, inosilicates. And so what happens is most lithium is gotten from lithium brines from South America. South America has brines that has lithium in it at about 2% concentration. And it takes about 18 months for these brines to evaporate, and then you go after them. You can get lithium brines in the United States. There's a region called the Smackover region that runs from Arkansas through East Texas, actually where we are here in Houston. It's part of the Smackover region. If you dig about 2 miles deep, you hit these brines, and there's brine concentration is about 0.25%. But there's a lot of work in that. Here, we can take these ores. These ores are about 5% lithium. When you look at the metal content, it's silicon, aluminum, and lithium. It's about 5% lithium. Here's the thermodynamic plot. Remember, whatever is below 0 is going to be an active reaction. And so at about 515 degrees, lithium will chlorinate and form lithium chloride. before aluminum and silicon ever chlorinate. And then the boiling point of lithium chloride is about 1,500 degrees, slightly over 1,500. So if you just chlorinate at this temperature, boom, it's going to come distilling out. And what we can get out here is a purity of about 95% purity, about 92% yield on the lithium. Just directly taking this ore that's found in the United States. We have lithium on the East Coast and on the West Coast of the United States. If you want to do it from ore, you can do it from ore. We've done it from battery waste. All of these options are open to us. Niobium and tantalum. Again, this is the commercial process that is used for taking this tantalum niobium ore. And Michael, who's here with us on the call, told us that, hey, there's a large interest in niobium, and there's this compound called cobalt, and it also has tantalum. The tantalum has higher value than niobium. But this is the process that's used today. We're really going to shorten this process. So here's this cobalt, and you can see we're able to isolate 84% purity of niobium from this reaction, and now we're going after the tantalum as well. So we're pulling this thing apart. I don't have the specs on this, on the yields, and because we haven't determined that. We still have yet to run what's called the ICP MES spec to be able to determine that. But you can see that we can start to do this even from ores. How about doing this for an industrial waste management? Lots of industrial waste is generated around the world. This is red mud. When you make aluminum, how do you make aluminum? You don't pull aluminum metal out of the ground. No, this is a formed metal. And so what you do is you pull out aluminum oxide, and then you take carbon. Carbon is usually something called metallurgical coke. It's a coal product, and it's cold. It's heated and compressed, and you use that as a sacrificial electrode. And you're putting the aluminum oxide with carbon, and the aluminum oxide is being reduced to aluminum metal, while the carbon in the coal gets oxidized to carbon in the coal gets oxidized to CO2 in the process, and you use a lot of electricity, and so you build a power plant next to your aluminum mine, and that's how aluminum is made. There's a lot of energy in making aluminum. There's a byproduct in making aluminum, and that's called red mud, or bauxite residue is the formal name. The common name is red mud. It looks red. It looks red because it contains iron oxide in the form of hematite, and hematite is red, and you see as far as the eye can see. And this is a toxic waste, and they just accumulate toxic waste all over the world through this. And this has so much iron in it, we can't get the aluminum out of it anymore. It's called the tailings. It's got aluminum there, but there's so much iron in it, we can't get it out. So can we just remove the iron from this? And the answer is yes. You see that it's got about 45% iron, and it's still got over 20% aluminum. So if you look at the plot here, here's where the different metals are, and here's the different metals. And what we're going to do is we're going to chlorinate at 1450, and we're going to try to get rid of the iron in this. And so what we can do, here's the traditional route for doing this. It's a lot of work. You take the red mud, mix it with lime, which is calcium oxide, mix it with a reductant and sodium carbonate, and put it in a mixer, heat it up very hot in a roaster, then crush it, and then put it in a magnetic separator, and then dissolve it up, and then do this hydrolysis and roasting again. And here's what we're going to do. We take the red mud, and we do this chlorination with Joule heating at 1450 degrees, and boom, we get rid of the iron, copper, nickel, magnesium, and sodium, as well as the heavy metals. Those all come out as well, and we're just left with aluminum, titanium, and silicon, and this can go right back into the normal process again for treating aluminum oxide, converting it to aluminum. So this is the process, and what we can do is in this flash we can go ahead and we can remove all of this iron in the volatile phase. So we just pull it all out, and our residue just has about 5% iron left in it. And again, this is just the first demonstration in a laboratory, and from this, Michael and Steve will talk about what they're setting up in India to do this. How about flash Joule heating with chlorination for separation of rare earth elements? So we want to actually separate them. So you have many rare earth elements, and rare earth elements aren't really rare on Earth, but they're hard to separate. And so if you look at where are rare earth elements, so here are rare earth elements. For example, a fighter jet, a F-35 fighter jet has 0.4 tons of rare earth elements in it. This destroyer has 2.36 tons of rare earth elements. Here's a Virginia-class submarine, 4 tons of rare earth elements. And it's in our missiles, our UAVs, our smart bombs, our radars, our electric vehicles, wind turbines, motors, phosphors, solar panels have to have rare earth elements. We have to be able to get those to separate. And this is what we're doing. We're working on the separation. There are companies that have processing lines over 500 meters long. Think of more than 5 football fields long are the processing to try to separate rare earth elements. And we're trying to compress that down. And so that's what we're doing with this process. And hopefully we will do that in collaboration with MTM and Flash Metals USA. Because of you, millions of people have heard the gospel. If you confess with your mouth Jesus is Lord and believe in your heart that he's risen from the dead, and you will be saved.
That's right.
That's the requirement. We talk about science concepts which draw people in. Take these nanomachines and have them drill into cells. This would be a great way to kill cancer, right? We also talk about Jesus Christ, who's the best in everything. My faith in Jesus Christ means more to me than anything. If you could continue to give or give for the first time, we would certainly appreciate it. You can go to jesusandscience.org. Thank you so much. So what I'd like to do is now look to Steve and Michael to start sharing with us about the company, the parent company, MTM Critical Metals, and the entity in the United States, and how you're building this here in Houston. And just take it from here. Tell me about the company and things, and then I'll ask you questions about that afterward. And when you start, if you could introduce yourselves and tell us your background, because I want the people to see that both of you have an engineering background, so you understand the technology. So not only have you worked on the business side, but you have that engineering background, which enables you to understand what I've been talking about. So I turn it over to you guys from here.
Yeah, Steve, do you want to kick off?
Sure. Thank you, Jim. That was an excellent overview and very, very easy to understand how the technology is all coming together and working. I also agree with you. It's interesting that we have a company that is run by 2 engineers. Michael and I are both chemical engineers, but we've also spent a lot of time learning the business side of things too. But the combination is very helpful in this area. So I'm a chemical engineer from Vanderbilt University. I've spent about 30 years in the recycling industry, both in the U.S. and then also based in Europe and Asia. And I've built over 100 recycling plants globally. And I've done a few engagements where I was the CEO of private equity-backed businesses as well. And I joined MTM about 1.5 years ago, and I'm really enjoying it. As Dr. Tour has explained, the technology is a true disruptor in the mining and metallurgical space, and that's really what attracted me to join the business. Michael, do you want to explain your background?
Yeah, sure, yeah. And yeah, thanks, Dr. Tour, for the invite. You see, I'm a chemical engineer as well. I got my degree in University College Dublin, but I'm based in Australia for nearly 15 years now. And my background was originally in pharmaceuticals, so scaling up drugs that Pfizer were making in the lab to commercial scale. And after a few years, I got involved in waste-to-energy technologies, again, early stage commercializing waste-to-energy technologies, pyrolysis, gasification, and these type of techs. And then I spent the last 10 years before I got into the public company space. I spent the last 10 years in mineral processing technology, and primarily with the world's biggest player in that space called Outotec. They're now called Metso, out of Finland, and they're pretty much involved with all of the world's mining projects in some shape or form, in pretty much every single technology, taking an ore body all the way from in the mine where you're blasting the material into smaller particles, all the way to a finished refined product, and every single technology in between. So I've been in the technology commercialization and mineral processing for over 10 years. And more recently to that, I got involved in the public company space here on the Australian Stock Exchange. And that's what led me to MTM, originally as an advisor to MTM, this listed company, which was originally a mining-based company. And as soon as I saw what the technology could do, in particular on spodumene and revolutionizing how spodumene, the main ore that lithium comes from. And when I saw the kind of breakthrough potential that the technology had, that's what convinced me to take on the CEO role at MTM, which is the parent company listed on the Australian Stock Exchange. And the good thing about being a public listed company is that we've got much bigger access to capital than most private companies do, because we're publicly traded. Being publicly traded means we have to adhere to very strict, I suppose, reporting and auditing type requirements, so that the money we do raise, people trust that we will put it to good use. And yeah, we're very excited to be commercializing this technology. As I said, it's got almost across the periodic table of metals. It's now shown really favorable opportunities to essentially change how the traditional methods, which have been around for over 100 years, like the rotary kiln, the fluidized bed. So these old systems that a lot of mining companies are wanting to transition away from, burning fossil fuels. They would prefer to use electrical-based energy if they can use renewable energy, for example. So that's what one element that the flash heating technology offers. But yeah, primarily, and another thing that Dr. Tour mentioned is, so being chemical engineers, one of the fundamental things that you are taught early on is scaling up from the laboratory to full scale. That's the main fundamental job of a chemical engineer, scale up, and that's what I suppose attracted both myself and Steve to this venture now, taking what Dr. Tour has pioneered in the lab to the industrial scale.
Right. So let me just give a little bit of background. So again, remember, we take these technologies, run them on a small scale, we file a disclosure. A month later, that's turned into a patent application that's filed, and then we start looking for an investor group that'll launch this. And Steve came on board before it ever was paired with a public company, and then there was this reverse merger with MTM to take this on. And so Michael or Steve, could you just kind of walk us through those steps? How does it go from being this private little thing that started with some angel capital, some small investment from a few people that allows you to hire a person and start thinking about technology, and then how does this reverse merger work with a public company?
Yeah, sure. So I think fundamentally you have to find the right vehicle for it, and typically the right vehicle, especially in an early stage for technology, is something that's got a low valuation. And on the Australian Stock Exchange, the general investor base is quite interested in metals and mining related investment. And it's just the history of the country. It's a mining rich nation. And a lot of the punters, the investors on the Australian Stock Exchange, have some exposure to metals. So the Australian Stock Exchange was a natural choice for this type of venture, picking a suitable exchange. And then the second thing is that venture type funding in Australia is quite different to how it's done in the US. And generally speaking, the Australian investor would be considered much more of a risk taker than the general US investor, who they might need to see a market capitalization of a company, over $1 billion, $10 billion before they're even willing to look at it, whereas it's a different proposition on the Australian Stock Exchange. So that leads us to then, if you get a vehicle that's got a low valuation, like a lot of the mining exploration companies, who the sentiment towards exploration and appetite for investment in exploration has really dwindled over the last, say, 5 years. And that then creates what's called essentially a shell company, where the value is almost, you've got cash backing, you're being valued for the cash that you have in the bank. So that people who have a technology, they see that as a real opportunity to create shareholder wealth by, if you get something in at low value, and if you can convince the market that it's got real commerciality, then you can get potentially, 10, 100, 500, 1,000 times your original investment. So that's the attraction of, if you put in the risk, technology commercialization is risky, but if you find the right vehicle and the right investor base, you really can make life-changing returns if you get in at the right time. And I think, we've certainly had quite an appreciation in the last, say, 12 months in MTM's market capitalization, as we've taken investors on the journey from, initially educating what this technology could do, to now having real commercial contracts with supply agreements. We've now got a site in Texas, so it's all becoming more real as we and the valuation is appreciating at the same time. So really, it's about finding the right shell, and then, but you need to have the right investors too, who are willing to take on quite an element of risk in the early stages, because in reality we're not commercially producing revenues yet, but we do hope to be by first half of next year. So yeah, finding the right investor and finding the right vehicle.
So then you started a U.S. entity called Flash Metals USA Inc. in Texas, in the Houston area. Why did you choose Houston? And what kind of partnerships did you need to begin to transition this from these little reactors in a little laboratory, in a nano lab at Rice University, to think about big scale and how you're doing it? How do you take it these steps?
Yeah, I think Houston made sense. It was very practical. Houston's actually a pretty strong market for technology type startups, and there's a good environment in Texas in general and Houston specifically. And we also were fortunate in that we had a relationship with an engineering firm, a very interesting engineering firm that's very high end, working with NASA and Chevron and many of the big oil companies, Sasol out of South Africa. They solve very difficult technical problems in high temperature operations like flash Joule heating. So Nighthawk is based in Houston, and based on our relationship with Nighthawk, we extended our team dramatically out by 15 or 20 people, all very skilled in multiple disciplines. So we punch above our weight very quickly based on our relationship with Nighthawk. And then, of course, the relationship with Rice University and the interplay with Dr. Tour and his team is also very important. And because they're here in Houston, that really helped us go that way. And then just the general petrochemical complex is a great support with potential investors, but also people that know how to build things and get things done. Michael, did you want to add to that?
I think, yeah, from a non-US citizen, I think Texas seems to be a very pro-business state, just compared to several other states and countries. And yeah, even the place that we're now in, Anahuac County, we've got immediate interest and welcome from the local council. And there's also significant grant opportunities available. And a lot of the Texas-based congressmen have all agreed to give us letters of support for these big grants that we're targeting with the DOD and the DOE. So yeah, Texas is it's where you want to be to do the type of business we're in.
Right. So actually, let me say at this point, lest I forget, that I'm never an officer or a director. I'm not an employee in any one of the companies that I start because of conflict of interest terms. I have to stay separate from the company, so I don't make decisions for the companies. They run on their own. I will give them scientific advice. Usually that's just in the beginning. And then after 6 months or a year, they're ahead of me anyway. They don't really need my advice, or they've hired my students, and my students know more about these topics than I do anyway, because they're the ones that have educated me. And so they're up and running in that way. So they've gotten a big facility. I think you can correct me, but I think it's over 30,000 square foot facility in Anahuac, Texas, which is in Chambers County, which is just east of Houston, very close to the Houston ship channel. So when you're close to that ship channel, that's like one of the major ports in the world for moving chemicals in and out of. So they have ready access to that. And they have ready access to so there's some pictures of it. There's the facility there, that campus, and you can see that they've already got that. So they'll tell you a little bit about that and what they've got at this site and what their permits are, because this is a very big deal. When companies want to start, you're like, where do I start? How do I set this thing up? And we looked at little incubators here associated with the university. It wasn't right for this, because this is a big operation we want to start, and we don't want to spend years doing development, because we've already sort of done the development work here at Rice. Nighthawk has taken this over the last year and a half, which is an engineering firm, and a contract engineering firm and started building a larger scale system. They came into Rice, they saw how we built this, and then they took it and they scaled it up from there. They hired one of my former students who helped design this equipment, and they moved into this facility. So take it from here. Tell us about this facility. Tell us about the permitting. Tell us about the agreements you have on moving material in and out, and these floor pricing agreements, and what all this means. It's really quite elaborate, and but it'll give our viewers an idea of the steps that need to be taken when you go from a little nanotech lab and you go into an operation like this.
When you want to build a plant, some of the things that investors are interested in are how are you going to obtain your raw materials? We call that the inbound supply or the inbound supply agreements and the commercial terms surrounding those. And then there's the outbound, which are the offtake agreements or the sales for the recovered metals in this case, or the recovered syngas that comes off the plastic. And so you have to put together basically a network or a set of pieces that fit together where you can guarantee or have confidence that you're going to have enough inbound supply of raw material to run your plant all year long, or to meet your financial goals, your production goals, and also have outbound contracts at pricing that will make sure you can make a profit in between what you're paying for your raw material and your outbound sales. So we're fortunate enough that we have relationships with a number of large electronic scrap recycling entities in the U.S., and we've signed them up on letters of intent, and we're finalizing contracts with them now to supply us with printed circuit boards for the inbound raw material. We also are working on supply agreements for production scrap from semiconductor manufacturing, so things that would have a gallium or indium paste or indium tin scrap, things like that, which we'll bring in, use the flash Joule heating and the chlorination to extract the metals, and then sell the metals. So we have a full suite of inbound contracts, supply contracts that we're working on, and outbound offtake agreements. So that pulls everything together so that we can explain to our investors how the economics of the business will work. At the same time, we're working with Nighthawk to build out the equipment and deliver it to the site, this particular site in Anahuac, Texas. The equipment will start arriving in November, December, and we'll be processing electronic scrap and gallium and semiconductor material at the site come January time next year. So very rapid implementation. Michael, did you want to go ahead and add to some of that?
Yeah, and just maybe mention, Steve, that like the commerciality of some of the agreements are really important. And we've fortunately have a very mature client that we have in MTM Corporation who we're currently talking to regarding the supply agreements. And the mature thinking around that is that we will have minimum floor pricing for some of these metals like gallium, germanium. And what that does is protect us against any nefarious ulterior people who might want to manipulate the market. And China has often done this several times in several metals, including rare earth elements and gallium in the past. But to protect the business and protect what we're trying to do, the floor pricing would give you a minimum price that at least allows you to meet your operating costs and some margin. And also the agreements we're aiming for will also not cap the upside, so that we're incentivized to still trade our material to our partner MTM and not sell the materials when the prices are high to someone else. So it's a very mature way of thinking. We're fortunate that this particular group, MTM Corp, is a very seasoned player who've been around since the 1930s. So these type of considerations.
You know, the other thing to say is that investors like businesses that are hedged out in a particular way. It's a word we use, hedged out. But what happens with the printed circuit boards is if the price of copper and gold and gallium goes down, as commodity prices do, they go up and down. As the price goes down, we pay less to the recyclers that are collecting the printed circuit boards. The price we pay them goes down. And then as the price of copper or gold or gallium goes back up in a market cycle, a commodity market cycle, we pay more for the printed circuit boards. So the spread, the gross margin spread between what we pay for the printed circuit boards coming in the front door and what we sell our basket of metals for out the back door is fairly consistent. It goes up a bit in a higher market, but we really have a hedged out model based on the ability to manipulate the price up and down based on commodity sales values. And that's how the market in the U.S. for printed circuit board works in general. So we're in that market, which is quite large. It's 4 or 5 million tons a year, and it functions quite well based on moving up and down on commodity price changes.
All right, so let me just make sure people understand this floor pricing and these protections, because what happens is these critical metals have become deemed critical because, for example, China is no longer selling these to us, so we have to have these. But what happens if we start producing an outlet for these and we can start producing these? What China could do, or any other player, could drop their prices dramatically because they already have all their equipment paid for. It's very mature on their end. They could drop their prices to way below what we might be able to produce these at, and drive us out of business. And then when we're out of business, then bring the prices back up in the market. This sort of thing is done. But by having a guaranteed floor price, this means that we're guaranteed that somebody is going to buy this. There are companies that have guaranteed to pay us for this. So regardless of what happens from these other players, and that then protects, say, U.S. industry from these sort of manipulations that foreign governments could do to take us out. So having these agreements in place, again, this is not something that Jim Tour thought of. I'm not a business person. This is things that Steve and Michael have thought of and built into this, because Steve comes out of the waste recycling industry and he knows how to do this and he knows how to set these things up. And then the other thing around this is the idea that you've chosen certain metals. What made you choose the metals that you're going to be going after first?
I would say there's two groupings, and we have 7 or 8 areas that we could go to first. We could go after red mud, processing to recover aluminum and titanium and rare earths, or we could process the concentrates, mining tailings from rare earth element mining. And we chose the combination of printed circuit boards as well as semiconductor manufacturing scrap based on the inherent value of the metals in those scrap materials and the availability of them. The fact that there's 4 to 5 million tons a year of printed circuit boards in the U.S., and the fact that 80 or 85% or higher of those printed circuit boards get sent export to Asia and other markets for recycling led us to really want to focus in as a priority on this e-scrap from semiconductor production scrap and from printed circuit boards in the U.S. It's called onshoring. And as Dr. Tour correctly has identified, many companies that are manufacturing semiconductor chips and high-end electronics in the U.S. are willing to pay a little bit more for solder or other materials if it's manufactured or the raw materials are coming from U.S. sources and being refined in the U.S. because they want to hedge on their own raw materials for their making of the semiconductors against an embargo from China. So they might say, we'll pay you more for your solder for a third of what we buy during a down market so that we can ensure that the supply through MTM and Flash Metals USA will continue even if the Chinese or others have reduced the value of the material. So anyway, Jim, that's kind of a long way to say you're correct. And the consuming customers, the customers that make these semiconductor devices, want to have a supply from the U.S. for part of their raw material furnish.
And I'll just quickly chime in on why we're so keen on both this gallium germanium waste and also this gold-rich electronic waste. So if I just focus on the gallium germanium material, first of all, so the material that we've got access to is about 15% by weight or mass gallium and 18% germanium. Now, if you think that the majority of the world's gallium and germanium actually comes as a very, very minor byproduct from bauxite mining or zinc mining. And I'll just quickly skip to show what a typical bauxite mine, sorry, it's not in this particular deck, but what a typical gallium in an ore body in the earth is about 50 parts per million. Or that's grams per ton. And it's something similar for germanium. And that's typically in either a bauxite ore body where it's not the primary metal, or it's in a zinc ore body where, again, it's not the primary metal, but it's a very minor byproduct. This material, 15% weight is 150,000 ppm. So that's 50 ppm versus 150,000. So you can see why we're very keen on this type of waste, this urban mine versus the traditional mine. And in a similar manner, these gold-rich electronic printed circuit boards. So some of the material we've recently tested have over 500 grams per ton gold. A typical, the global average for gold in the ground in an ore body is about 2 grams per ton currently. And a 2 gram per ton gold mine is economic in an open pit sense these days. So 500 versus 2. So you can see why we're very interested in this urban mine waste. And again, with a typical mine, you first have to put a lot of effort and typically tens to hundreds of millions of dollars to find the deposits in the first place. And most of the easy deposits now have been found. So it's getting harder and harder to find fresh new ore bodies in the ground. That's why we're so excited about waste, because these metals have already been found and discovered and mined. So it's much easier to get metals from waste rather than finding them in the Earth's crust.
Yes, and the other thing, Dr. Tour, we should mention is that, as an example, in a rough math in the United States, maybe only 1 out of 4 or 1 out of 5 computers get recycled, or electronic items get recycled. So the recovery rate or the recycling rate is in that 20 or 25% or lower, and consequently there's still an untapped resource of dramatic size in the U.S. as we build out these processing and refining plants in the U.S.
Right, and every time you store something to the cloud, or every time you have Grok or ChatGPT do a calculation, these are going through server farms that are filled with printed circuit boards. And so every time you store something, every time you save something to the cloud, it's saved on a device, on a printed circuit board, in a server farm. And those server farms replace out the printed circuit boards about every 3 years. So there are mountains of printed circuit boards that used to get shipped off to other countries for reprocessing. We have them right here. And we're building all these more server farms and server farms for AI processing in the United States. We have this amazing source of material right here. There's no need to be doing this mining and bringing all the heavy equipment first to identify the mine. As Michael said, it's hundreds of millions of dollars just to find the mine, and then hundreds of millions of dollars to start mining those and bringing in the equipment and paying for all of this. And then you saw all the steps of processing that are needed when you go from the ores. Whereas we have these compounds already separated in 1,000 times higher concentration than what you find in the ores. It's 1,000 times more concentrated. So it's right here among us. That's what we call urban mining from what we've got right here. And that's what this company is going to be doing. That's the whole idea, to do the urban mining. We have it all. And when you retire one of these aircraft, when you retire one of these systems, you just pull the metals right back out through this easy flashing process and go right back in. So environmentally, it's a huge plus. And so we have the environmental factor here as well. What I want you to touch on too is tell us about the pre-permitting that you had with this facility that you got here in Texas, in Chambers County, Anahuac, Texas, and why is pre-permitting so important? How long does it normally take, and what's the advantage of doing that here in Texas?
Yeah, I think that's a very interesting point to make. And, it's the general theme is that understanding your market in detail is very important in any endeavor, any business endeavor you're starting up. And we're fortunate enough that we understand the solid waste and hazardous waste and the recycling markets very well. And we were able to find this particular site and value it, this site in Anahuac, Texas, about an hour east of Houston. And Texas is interesting in that when you have a hazardous waste permit or other similar types of permits associated with a given address or with a given site, the permit tends to stay with the site, get assigned to the site, rather than with the entity that has been using it. And there's some exceptions, but in our case, that's true. So Texas is very pro getting things done, getting new companies developed, new industries developed, and these types of permitting approaches allow for companies to understand, okay, we have a building, we can put our equipment in there and use it without having to wait 12 or 18 or 24 months for a new permit. So the speed and the surety, the comfort of how things work really helps Texas develop new businesses quickly.
Michael, there's one mistake on this map that you're showing. That Gulf of Mexico has been renamed. So that's the Gulf of America. So we're right next to the Gulf of America there.
Yes.
I won't be allowed back into the U.S. now when I get to immigration. Yeah.
So let me ask you to now tell us what you're doing on the industrial waste side with India. Is this processing you're going to do for them, or you don't want to be shipping this red mud from India to the United States for processing? So how does this work?
Yeah, and I think we should mention too that as we've been looking at applying the technology, the flash Joule heating, and actually working with industrial partners on taking their raw materials, their byproducts, their waste streams, and testing them, we've learned interesting things. So the most interesting thing about red mud, well, first of all, we have to set the stage. So in the world today, when you make aluminum, by and large, you're making it out of raw bauxite that gets mined out of the ground, and you use the Bayer process to convert it into alumina. And when you do that, you generate a waste stream, a byproduct called red mud. And if you take the roughly 150 million tons a year of red mud that's generated globally every year, and you put it in trucks, put the red mud in trucks and line them up, they'll go around the earth more than 4 times. And 98% of that material is not being reused today. So as we tested it, as Dr. Tour laid out earlier in this podcast, we found that we can remove the iron, we can recover iron chloride, recover titanium chloride, and then we can recover aluminum, and all of those things have great value. But in the beginning, we were a little bit worried because we still had this material left that didn't have value and that would still have to go in a landfill or an impoundment. And we worked with some very good partners out of India called Vedanta and some out of Brazil. And they have figured out that if we, MTM, when we remove the iron at a certain ratio, they can use what's left as a clinker substitute in making cement. And then all of a sudden the light bulb went off for us and we're like, okay, this is a real business. We can extract iron and there's value there. It has, call it $2,000 a ton iron chloride value. We can extract titanium, very high value and in demand. And then aluminum, of course, has high value. And we don't have to get it all out. We don't have to recover all of it. We don't have to be perfect. As long as we recover a majority of it in the ratio that the cement company wants, we're in good shape. And then the final key, the final piece of the puzzle, which Michael Walsh really helped figure out, is that if we can reduce the basicness of it, not acid, but the base side, meaning can we remove the sodium from the red mud and get it to be less of a basic material, less of a caustic material, the cement companies really like that because they can use more of it. And sure enough, using the flash Joule heating, we were able to remove the sodium at 90+%. So long story short, with the Vedanta team in India, they're quite interested in treating their red mud and getting it into a cement format, which is in line with some of the fiscal and government goals that are emerging over there. And that opportunity is also the case in a number of other countries in the world. So we're very excited about that industrial use of flash Joule heating. And there are a couple of others that we can discuss. I don't know, Michael, if you want to mention the rare earth element tailings and concentrates, or maybe even the spodumene.
Yeah, sure. So another really interesting application is refractory mineral processing. So refractory just means hard to liberate. And generally liberate means that you want to expose in an ore body, there's the target metal and then there's all these unwanted, what they're called gang metals in the lingo in the industry. You want to remove the gang unwanted deleterious elements and you want to enrich the target metal. So with lithium, and Dr. Tour mentioned spodumene. So spodumene is the mineral that lithium is within. So it's lithium stuck to a silica stuck to an aluminium atom, and there's often iron in there as well. And everything else is an impurity, and you want to concentrate the lithium. And the traditional flow sheet is you produce a concentrate which involves crushing the ore, then grinding it down to about 150 microns. So very, very small particle size in a big ball mill or a sag mill. And then there's several stages of sizing where you pick out the different size fractions, and the smaller size fractions go through a flotation plant where these gang elements are depressed and they sink, and then the target spodumene atoms, when you add reagents, they float to the top, and that's called flotation. And then there's more steps, and what you end up at the end is you go from the natural ore is about 1.5% lithium oxide, and the spodumene concentrate is about 6%. So you go to a big effort, and you only really get about a 3 to 4 enrichment ratio from the ore. So you get a lot of effort to get the spodumene concentrate, and typically then all the downstream value adding currently is done in China, and because it's very energy intensive, it's done in calcination kilns and acid roasting kilns, where you cook the material in a calciner for about 3 hours at 1200 degrees Celsius. All of these kilns can only burn fossil fuels, so they're very carbon intensive. And then once it's calcined, the spodumene expands, and if you don't do that calcination, the spodumene is so refractory, no amount of acid will leach it because it's so tightly stuck to the silica. So once it's expanded and calcined, then you have to put it into another acid roasting kiln at about 300 degrees, again for a few hours. And this is where you add lots of sulfuric acid. But there is all the impurities from the ore body are still in there. So when you add sulfuric acid to those impurities, it causes all of those to also go in and react with the acid. And then you have to spend lots of steps. And sometimes it's up to 20 or 30 steps of impurity removal steps, which is very capex and opex intensive. And then you have to go through an ion exchange process, evaporation, etc. And to get to your final battery grade lithium carbonate that goes into the cathode side of a battery. So it's quite a convoluted, energy intensive flow sheet. But the majority of the energy comes in that calcination step. And one of the first potential applications we thought of was to see, can we just compete with flash Joule heating on that calcination? Can we reduce the time from 3 hours to something more favorable? And we demonstrated that we got a sample of concentrate from a mine here in Western Australia, and we achieved that calcination. Its technical term is alpha to beta shift, and we did it in a matter of minutes using flash heating with no chlorine at this stage. So that was a big tick. But then the real revolution happened when we added chlorine, once we've licensed the chlorination from Dr. Tour, and that's where we effectively distilled off the lithium from spodumene concentrate as lithium chloride. And then in theory, there's only one more step to go to lithium carbonate. So you effectively could, even up to 90% of the capex and opex of the traditional Chinese-based flow sheet could be reduced by implementing a flash Joule heating type solution where you vaporize the lithium as lithium chloride. So that was the real breakthrough in my head for how I thought that this is a real breakthrough technology. And then there are similar, equally compelling arguments for monazite processing. Monazite is the main mineral that neodymium and praseodymium comes from in Western Australia and elsewhere in the world. That's the main source. Monazite is the mineral. There's also bastnasite is another mineral that's rich in neodymium, praseodymium. But with monazite, again, it's sulfuric acid and kilns. And with the flash Joule heating method, we reckon we can cut out those kiln-based steps, and instead of making rare earth sulfates, make rare earth chlorides, which are much more soluble in water. You use less water and you don't generate gypsum tailings. So there's several economic and environmental benefits from what we can articulate from using flash Joule heating compared to the traditional sulfuric acid kiln-based fossil fuel burning approaches.
Yeah,
Good.
and when you think about that, one of my favorite parts about our business as we develop it is the fact that we are an enhancement. We enhance some existing unit operations and capital deployments for companies such as rare earth element refiners or spodumene refiners that are recovering lithium. And what I mean by that is many of these mineral processors and even e-scrap processors don't really get value out of the fines, F-I-N-E-S, the small material that gets created when you grind up other minerals and e-scrap. And we have found that the flash Joule heating approach, the MTM approach, is really very well suited to recovering high-value metals out of fines. And what this means is that there's this concept of EVA, economic value added, in business. And a lot of these existing very large industrial refining plants, if we can pull the fines out and recover metals efficiently, their capacity, they reveal capacity in their large kilns. So if we take 15% of the volume going through an existing kiln and we process it as a fine, or the fines, using flash Joule heating off to the side with a new system, much less capital, they can push 15% more normal ore through there, substituting where the fines used to be, and the return on capital on that existing asset goes up dramatically. So a number of these companies are very excited to work with MTM on processing the fines and tailings that they weren't getting any value or very low value out of in the past.
Right. So as I pull this together to a close, I want you two to just think of, a closing statement that you might have, something that you want to mention before we close. And let me mention, because people have asked me about this. Hey, you use chlorine. How hard is that to use? Let me just say that chlorine is used in thousands and thousands of tons, probably millions of tons every year in the United States and around the world. It's a very common reagent, and it's highly accessible right there in the Houston Ship Channel. And it's a common reagent. It's a gas that's used, an industrial gas. And the whole infrastructure for using chlorine is extremely well figured out and very well developed. So you're not developing any new tools for the use of that. And the recycling of chlorine, the chlorine that went through the reactor but that did not react, is easily recycled and brought back around. So chemical engineers have figured this out a long time ago. So the chlorine is not a limiting factor at all. With that, let me ask you first, Steve, any closing thoughts that you wanted us to hold on to before we wrap this up?
Yeah, I would say my intuition about the business and applying flash Joule heating to metallurgical processes, and more importantly to scrap and recycling, is that we literally are just scratching the surface on the economic value and the ways that this approach will be used to enhance industry and make it more efficient and onshore the refining in the U.S. And then the second thing that I'd like to say is something, Dr. Tour, that you presented or invented at the saying was at the COSM conference in Seattle last year in November, which is that we're turning trash into cash in a flash. So we'll attribute that quote to you, and we love the way that is providing an insight to what we're doing.
Yeah, maybe I would just say that our ambitions really are to scale up this technology as quick as possible and commercialize it as quick as possible. And if we take just the printed circuit board feedstock as our base case, then, and if we realize getting our ambitions over the next 2 years of getting a significant portion of these printed circuit boards in the United States, in theory, we could be in the top 5 gold producing companies on the Australian Stock Exchange within, a couple of years. So that's we would be a very valuable company if we can achieve that. And then the other point is that I think if you're an up and coming student who's interested in chemistry or physics and you want to have a pathway to not just be stuck in a lab for the rest of your life, then you should go to Rice University and study under Dr. Tour.
Absolutely. Hear, hear.
Thank you. Let me just ask you one more question, Michael, about this. You're on the Australian Stock Exchange, which you can access through the U.S. Stock Exchange, but through this MTM CF. But is there intent in the coming years, if you want to start raising more money, that you would transfer this to the U.S. Stock Exchange and put it on the U.S. market in total in that way?
Yeah, no, we are in the early stages of looking into that onto a NASDAQ listing in the United States. Mm-hmm. So the more we can grow our market capitalization, the more we can justify such a transition. But yeah, we've definitely been looking into it already, and some of our peer companies have already successfully done that.
Mm-hmm. Yeah, and Michael, we should confirm that our stock ticker, if people have strategies or they like to make investments in different companies, we are MTM on the ASX. The ticker is MTM on the ASX stock exchange, and then in the US we're MTM CF, and I always say MTM like center field, so MTM CF is the US based one.
Yeah.
Great.
So so what we've done is we've taken you through this sequence that goes from an academic lab, an experiment in an academic lab, and brought you through these sequence of steps, and then how this transitions into a company. So you see all of these different steps. And I think actually this is part of the motivation of the federal government right now, is to have more of this happening, to have these sorts of partnerships where we take the technology that we've developed in academic laboratories through taxpayer funds and see that transitioned into companies that then end up hiring people, building up the tax base, and then meeting critical demands that the nation has. And that's what we're trying to do, to try to bring it through all of these steps. And hopefully, this showed you the science side of this, and then the commercialization side of it as well. And that was the purpose of this to give people a view of how this happens. And I know that many academics have asked me, how does this happen? And so this is the sequence of events. With that, I want to thank you, Steve and Michael, for joining me on this podcast. And hopefully we can see great things happen for the country and the world together, as we can take mining and moving more to urban mining and access these critical metals and critical minerals more effectively. Thank you.
Thanks for the invite, Dr.
Thank you so much. Really appreciate it.
Thank you for joining me today. If you could give us a like, share, or podcast review, we would appreciate it. If you have any questions, you could send them to ask@jesusandscience.org, and we'll try to answer some of those questions in an upcoming video. And if you do not believe in the physical resurrection of Jesus Christ and you want to hear about why I believe, send me an email to tour@drjamestour.org, and we'll get together by Zoom, and I'll share with you why I embrace the resurrection of Jesus Christ.